Right, last talk of the morning and possibly the workshop, because we've nothing planned for tomorrow. It's a great pleasure to welcome Jake Taylor, who's going to talk on one of our favourite subjects, interconnecting quantum systems together with applications to measurement and control.
So it's actually been a great pleasure to be here at the Newton Institute, and I've had a cross-section with a number of people that I normally don't get a chance to talk with. So bringing physicists, mathematicians, and engineers into the same room with a common language, for me, has been essentially rare. I've really been enjoying the conversation. So thank you very much for putting this together, and I hope we get to do it again sometime. I'm going to talk today about some joint work with my student Tavira Caffrey and Gerard, looking at how we can take the concepts in quantum channels and quantum measurement and feedback and apply them to some specific physics challenges. A lot of what I'll talk about today is actually covered in 3 papers that are up on the archive with these authors in various permutations. And if you want some details, I encourage you to go there. My goal today is to give you some sense of our background motivation, some of the work that we've been able to achieve, some of the open questions that we now have, which hopefully I'll be able to put back to the control and feedback community to get some better ideas of how we might solve them. I encourage you to interrupt me in the course of my discussion. I'm giving a Blackboard talk in part because I hope you learn something, and in part because I hope I do get interrupted, so that I can actually learn something as well. I'm at the Joint Quantum Institute, which is a collaboration between the National Institute of Standards and Technology in Gaithersburg, Maryland, and the University of Maryland in College Park. But I'm also part of the Joint Center for Quantum Information and Computer Science, which we call QUICS, which is just getting off the ground now. And so if you want to come visit QUICS and Maryland and NIST for extended periods, please let me know. We have an extensive visitor program starting up. The goal of this new center, by the way, is essentially to try and connect computer scientists and information scientists with physicists, all of whom have a joint interest in the medium of quantum information. So my entry to this story occurred when I started asking myself the question, why is it that we're not bothered by a neutron traveling with the Earth's gravitational field getting dephased by the Earth? In other words, when I have 2 particles and interacting, under what limits do I not have to worry about the information transfer between these 2 particles? And what are the consequences of that observation? But that's a very abstract sort of physics notion. I need to translate it into an engineering language before it actually becomes concrete. So this, for me, was an example of where the literature and the engineering community dramatically changed my understanding of this simple question. So I guess the question you start with is, what is a force? What is an interaction between 2 particles? And there's some what's right?
Good place to ask that question. Either in
Yes. Well, so you might think, first start by just writing down a Hamiltonian with an interaction, some constant little g, between an operator acting in one chunk of Hilbert space, so particle in one point space, times an operator acting on a different particle in space. So the picture of this system is that I have a particle over here described by A and the conjugate to A, a particle over here described by B and the conjugate to B. And I like to think that wiggling A makes B wiggle. And it does so because of the interaction between the 2. Now, in some sense, that's a very crude cartoon picture of force. Now, there's many different ways to implement this. One way is to think like a quantum information scientist and try and send the information from here to here via such a force law. But you have to sort of restrict yourself and say, well, what I don't have is I don't have anything that's non-local. And the key point there is essentially that all the theories we think are physical are Lorentz invariant. And the consequence of Lorentz invariance is that field theories have to be local. So you may want to have an intermediate particle. So you take the information in A, you send it into some intermediary, which travels along, and then interacts with B. Of course, in physics, we call this gauge theory, where this is the gauge boson that connects the two particles. And in quantum information, we call this a phase gate, an ion-kicked phase gate. What do? You have your particle with its silver space on A. You have your particle with its silver space on B. And you have an ancilla, a boson. You make an interaction between the ancilla and A. You make an interaction between the ancilla and B. And then this is the sort of interesting part. You actually have to undo that interaction such that no information about A and B is left behind in this intermediary field. These boxes are unitaries, and this overall circuit looks like the following thing. It's e to the I beta A times little p, where p represents the ancilla field. So this displaces the ancilla at amount A. And then I have e to the I beta B hat times little x. This boosts the ancilla field. Then I sort of try and undo these operations, but in the wrong order. This is what happens in the so-called fast kick gate in ion trap computing. The key point you need to notice here is that this object is a unitary transformation of this object, which corresponds to e to the minus I beta A times this thing boosted, B plus A to B, B. And I have this thing here, e to the I, A, B. A and B commute, they're on different particles. A and P commute, I can split this up. And I find that the AP term here cancels this AP term, and I'm left with just e to the minus I, A to A to B, A hat, B hat. So this circuit here has implemented the object, which looks like e to the minus I tau H. But there's a different picture for understanding the same circuit. Consider what's happening to the ancilla. So the ancilla starts in some coherent state alpha. It gets displaced. So it goes to new state, which is alpha plus A to A, which really only makes sense if I start in an A eigenstate over here. So you can think of this, if I start with some A eigenstate, but the displacement operation is capturing the information of system A into the coherent state. It's a measurement. Given that measurement, I then apply a feedback. The feedback here is on system B. What is the feedback? Well, here's the value x that I just encoded, and I apply it to B. So it's actually, the first half of the circuit is measurement and feedback. And the field in the middle here is the measurement field. So to take that analogy a little bit further, let me remind you of this sort of kappa limited measurement and feedback procedure we just heard about last talk in a physical context. Consider, well, one side of an optical cavity, an object on a spring, light field coming in, light field coming out. This is optical mechanics. If you were at my tutorial 3 weeks ago, you remember this quite well, and if not, I'll assume that you sort of know what I'm writing about, and we'll get to an equation in a moment if you disagree with the equation if you don't like it. what you get for this system, if I look at the field quadratures of x and y, and add little x and p for this harmonic oscillator, I get equations of motion in the rotating frame of a pump laser, where there's some overall amplitude in here, and the equations of motion look like the following. Oh, by the way, the interaction here is of the form g a dagger a x, which I can rewrite as g alpha capital X little x after all the transformations one makes in optical mechanics. Okay. So this is the interaction between the cavity and harmonic oscillator. The cavity equations of motion now look like the following. X dot is going to be the detuning of the cavity times y, minus the decay outside of the single side of cavity mode, this left mirror, plus root kappa of x in the input operator formalism, and y dot is going to be minus delta x minus kappa over 2y plus root kappa y in, and then one more term from this, which looks like a force, g alpha rho x. So move to the Laplace domain for a moment, because we're going to look at what happens for y out. Right, so y out of this cavity is y in minus root kappa y. And in the Laplace domain, I can solve y exactly. And I get, ignoring the initial conditions and taking delta to 0, this is just sitting right on resonance, I get y in minus root kappa over s plus kappa over 2 times root kappa y in minus g alpha x, which we recognize as the phase shift I get when I hit a mirror. In the limit, by the way, where kappa is much larger than sort of the norm of a harmonic oscillator, so that I can neglect the s in this denominator, plus a term g times 2 times alpha over root kappa times low x. Lo and behold, when I have a Fabry-Perot cavity, and I sit directly in the resonance, and I shine light in, on the other quadrature of the field is the position information. I've hopefully surprised them. So that's a broadband picture. It's true only over bandwidth kappa. Outside that bandwidth, this theory starts to break down. But of course, everything that we do in input operator formalism implicitly assumes a finite bandwidth at a high frequency. Now I can take this output and I can send it along. I'll put a phase shift on it. And the phase shift has the role of taking minus y out and mapping it to x in of cavity 2. Here's cavity 2. Here's another mirror. This thing comes in. It's going to drive that mirror. What's the interaction? Well, if I look at this harmonic oscillator's motion, it has a little x2 and has a little p2. I find that p2 dot has the minus the derivative, looks like x2 of the potential of x2. That's the usual part. And then it has a forcing term, g alpha 2 times x2 of the cavity field, which again in the large bandwidth limit, we find that the x2 is just root kappa x in 2 divided by s plus kappa over 2, which is approximately this 2 over root kappa x in, which we mapped to be minus y out. And so this thing becomes y in minus 2g alpha 1 over root kappa 1 times x1. So lo lo and behold, I get a force by substituting this in on oscillator 2 from oscillator 1. This is the same math, really, that went into that circuit up there. If I just did the first two operations. So, of course, the next question is, how do I take this feedback circuit, which I unfortunately covered, and get the other two halves of that operation? So that I'd go from measurement and feedback to coherent interaction. And the general approach for doing this is essentially to make a resonance so that the light from here comes back to here. So you get a high bandwidth, very high frequency cavity. And the effective picture that you then get looks like the following. I have an interaction G alpha x1 plus x2 times a cavity mode capital X. And I have a high frequency cavity, omega, for 2 y squared plus x squared. And this frequency domain is going to be very, very high. Okay? If this, and then I have the harmonic oscillator movement. If this is my story, what I will do now is apply unitary transformation, so-called Polaron type transform, in which I move the x variable by an amount proportional to this term x1, x2. This unitary transformation takes x to x plus eta x1 plus x2. And it also has a side effect of taking, for example, P1 plus P2 to P1 plus P2 times plus 2 eta y. So do be careful about that. This part here, I choose eta equal to minus g over omega, which is the value you want, such that after the unitary transformation, the linear coupling between these two fields is gone. And having achieved that, I get an interaction g squared over 2 omega x1 plus x2 quantity squared in the system, plus terms that look like little p1, little p2 times y, plus y squared terms. And these turn out to go to 0 in a large omega limit. Right, so this is what we also call sometimes adiabatic elimination with an intermediary mode. And this is actually how you can derive the Coulomb interaction from the Dirac-Lagrangian. I integrate out the field modes, and I get Coulomb. So there's a very ubiquitous sense in which gauge fields sort of locally estimate and then apply force elsewhere. But they also have to return in order to make it a conservative story.
In your model, you have, from the first picture
Yes.
appearance of the gauge boson, it just seems to magically appear from A and then disappear at B. There's no source of these bosons.
Above.
Yeah.
Yes, that's correct.
Similarly, in this model, you've got a closed circuit, a closed input-output model. So,
Well, I've at least enclosed one quantized mode.
in the input-output theory, there's always something as environment coming in, as a source of the noise.
Yeah. So here, the point is, I can't.
And there's
do this.
always somewhere for the noise to
I have
go.
to actually do one thing extra to what I just wrote down here to make this work in the input operator formalism, which is actually where this term came from.
Yeah. There's nothing
Which is I have to add a
sustain
box. I have to add a box right here, which has a single oscillator mode in it. Has an internal degree of freedom. You think of this as we've talked about before, it's the simplest approximation to a very short delay.
Can you just remind me
Yes.
of your objective of the calculation?
Ah.
I kind of got a bit lost.
Oh, I'm sorry. So the point here is simply to provide a background and motivation, connecting the way in which the experimentalists think about input-operator formalism, the way quantum information theorists think about the way we apply gates, and the role that the connection rather measurement feedback can provide, and how we can use it by modifying this picture up here slightly. So it's actually trying to use the tools we have from channels and from measurement and feedback to constrain theories which break one of the assumptions that we normally have. So it's really a background at the moment. Now I'll get to the meat of it in about a moment. Yes, go ahead.
Well, maybe you're going to get to this, but of course it's not really measurement and feedback in the sense that, right, you're going to get to that.
Yeah, I'm still a bit confused as to what you're doing, because the picture you've drawn up there is not natural for feedback, right?
Well, I guess you might call this feed forward.
And you have a couple, optiomechanical systems that's very simple to write down, as you have the Heisenberg evolutions. It's just a pair of coupled oscillators. Right?
Yes. So the real question at the moment is, so if you think of this pair of coupled oscillators as now it's a quantum feedback model and it produces a force, purely coherent. This is actually a picture, you can also say, of the way the gauge theories work. This is one of the key points. But the other key point is that in order to turn it into measurement and feedback, all I have to do is not close the loop. In other words, the information that's being encoded in this field coming out goes into this cavity, causes a force. If I then never let it interact again with the first field, it's carrying a measurement current. And I could amplify it. I can actually do many things at this point. I could actually put this through classical amplification setup with homodyne and apply that homodyne output. So the quantum equivalent up here is to put right at this point here an operation S. It's a screen. It's an object which basically says whatever was happening in my measurement current, I turn it classical at this point.
What do you still call the a measurement? I don't understand that analogy.
Wait, which analogy?
The first one, what you're saying that that is like measurement feedback.
So again,
Obviously, everything is coherent there. Right? So.
up to this value S, everything's coherent. What did I do? I took information about operator A,
Yeah.
and I stored it, as I mentioned over here,
Sure.
in the field.
Sure.
Then I apply operator B by an amount proportional to the field value that is got stored.
Yeah.
So that's the feedback component. This is the measurement component.
Yeah, it's coherent feedback, so it's coherently encoded in the
Yes.
quantum state, and then so okay. So
Yes.
there's no measurement process. I want you to.
Well, if I let this field continue to propagate and essentially trace over it, or alternatively capture it as my measurement current, that's the measurement. In other words, the field
If you
is
trace
actually
over,
hearing this
what's the
information.
measurement?
What's
If you
that?
trace over that, there's no measurement.
If
Right?
you trace over it, then of course you just lose the dynamics. But if you keep it, then it's measurement.
Sure. If you measure, then it's measurement. Right?
No, I don't have to measure it. I mean, the point is I don't have to measure it. As long as it never interacts with the system again,
Yeah.
it carries the measurement record.
It's just like the Van Neumann measurement.
Yes, there's nothing. I mean, there's nothing deep.
Yeah, that's what Van Neumann called pre-measurement.
I mean, if you can think about the way an experimentalist interacts with an apparatus, it's simply that they take this thing, right, and then they amplify it. Right, that's this very weak current. You put it in an amplifier,
Yeah,
and
okay,
you get a kind of strong current.
But I'm still very concerned about some point here, because you've just set up an algebraic loop.
As again I mentioned, technically, in order for me to do this, I have to add one box in here.
No, you have to add in more inputs and outputs. In the SLH theory, in the network theory, we've seen that network has to be well posed before you can treat the algebraic loops. Now, if there are no further inputs and outputs, it's not a well posed algebraic loop.
That's true whether it's classical or quantum. The algebra has to make sense.
Yes, I don't disagree with you.
But you haven't drawn any more inputs or outputs.
Yeah, I guess it's
Yes.
physically
Yes.
unclear exactly what you're drawing there. That's
Yes, sure. I mean, the key point is that this is actually equivalent to one cavity with two springs.
But it's very,
Okay. the topology that you've got when you do this.
But what do you mean when you do this?
But that's
I'm
not
saying
an
when I hook
input-output
when I
model.
hook up the output of the cavity to the input of the other, and vice versa, in the large bandwidth limit, and I have this additional delay box I put in here, that is mathematically equivalent to this object.
But physically, you don't need a delay box because
Well,
there is a
physically,
delay, isn't it? I mean,
physically, the delay box is sort of incorporated in the finite bandwidth uses used here. I can't just put two mirrors directly adjacent to each other, right?
No.
I need some amount of vacuum in between.
I mean, I think all of these can be.
but that's just another cavity.
It is.
all of this-
What's the delay line?
Yeah.
Simplest example is another cavity.
Well, what are these boxes doing in the middle? They're virtual. I mean, I don't know.
They're purely mathematical. They're there just to sort of capture the essence of the argument.
But the inputs and output lines are described being basically your environment. What you're saying is somehow you can package the environment somehow into your system and have a seat in this connected model for the two oscillators.
Well,
the problem
okay,
is,
so if you want to go into the technical details of it,
what you've got there is something that's not a...
if you want to go into the technical details of it, I don't actually use SLAs to do this. That's part of the reason, right? The way I actually do this, and this is just a technical note, is I actually work with the following field theory. So I have a psi star d psi theory. This theory is a sort of chirally propagating one-dimensional mode. Okay? And then I can discretize it on any particular lattice length and recover these results. So I agree with you that the algebraic loop problem, if I use SLAs directly, is a problem. But I nonetheless find that once I've done this and matched the inputs and the outputs, I can throw away some problems in the algebraic problem as long as I concentrate myself in the Hilbert space that remains. So that's a pure practical application. But okay, that's a technical point, but we can go over it afterwards if you like.
Okay.
So if you're not familiar with this type of field theory, it leads to a wave equation, which corresponds to a one-dimensional propagation of information. It's analogous to the input field.
No, that's fine, but even in Lagrangian theory, you'd put in direct source terms. Here are no source terms for your field. Right?
Well, this field is going to be now, in this picture, it's going to be on a loop. Yeah? So it's going to be a field that propagates. So there's a boundary on the field that does this. And then I'll have a source term here and another source term here, associated with these objects.
It might help if you just redrew the picture as if it was in a real experiment.
Yes.
I mean, you've got most of it there, but I can't.
Sure. I mean, again, I have one-sided cavity. And I have another one-sided cavity. And there's springs in either sides. That's the experiment. So yes, there are no inputs and outputs anymore.
I think that's the point, it's a completely closed system.
Yes.
Your box around the whole thing, so there are no inputs.
Yes.
So is there anything in there?
How do you justify the
Otherwise it's
input
quite
output
easy.
problem? So you have no input and outputs?
Yes, there's vacuum.
That's what Jake is saying, just don't use it. Use the full field theory.
I mean, the fun thing is that I can now make a imposter box, S, which plays the role of the screen that you have above. And the imposter box is a very simple physical object. It essentially corresponds to a circulator. So here's light going in, light going out. There's a circulator. And then what you do is you make a heterodyne measurement on this thing. Yes. So I have heterodyne setups here. I take the output of the heterodyne and I use it to displace a coherent state coming in here, which I then send to the other side. And I have an opposite version with a heterodyne setup here. And I apologize, I'm running out of space in the corner of the port, which then produces a coherent state, which goes in here. What this box does is it captures those measurement outputs and sends them along. Now, what's that?
Approximately.
Approximately. You could ask why heterodyne? And this is an important question, which is why did I choose a heterodyne channel here? And it comes back to the question of force laws. So we need to take a brief diversion towards that end. If you don't mind, I'm actually going to work on this board for a moment. So why am I interested in only a particular subclass of these screens, S? That's really the question. So I'm interested in scenarios in which the interaction induced this way has a meaningful classical limit. And a meaningful classical limit, in a very simple sense, is a statement that the dynamics generated by this object, so call this circuit via some superoperator. Well, via superoperator once I trace over A anyway. The dynamics generated by this object should have the property that if I look at Heisenberg equations in motion for operator A and its conjugate, and B and its conjugate, that the expectation values should be describable by a classical Lagrangian, a classical Hamiltonian, within an approximation that involves this plus higher order corrections.
Is this some sort of Ehrenfest?
This is the Ehrenfest theorem. And so it turns out that if you want a screen in the middle here, which is allowed to reproduce Ehrenfest dynamics in a semi-classical limit, the screen has to do something very particular, which is that the action of the screen on the operator x of the ancilla minus x has to be 0. Similarly, the action of the screen on the operator p minus p has to be 0.
If you say higher order, what is the small parameter that you?
The higher order is h bar, is the small parameter.
It's h bar what? Sorry.
Yes.
That there is no something like speed of the propagation of the field or something like that.
No, it has to do with correlations. So the quantum corrections to the Ehrenfest picture. But the most important point is simply the following. If I want my screen to be able to reproduce something that looks in the classical limit like a force, I actually require that the screen take quadratures of the field and map them to themselves in the sense of that looks like the output of a measurement. And there are many things that do this. The thing that does this optimally is heterodyne measurement, followed by creation of a coherent state. Yes, go ahead.
Why do you want to put the screen at that particular point?
Well, you could put more screens in. You could put
Yeah.
one here and
Yeah.
here.
So why, well, if it's why do you want to screen that all?
Right, so the question is really the following. How do I distinguish a classical force from a quantum force?
So then why wouldn't you put a screen in every point?
It turns out that that's more screening than you need.
Okay.
So I'm going to say
Yeah.
I'm going to define particles are interacting in a classical way if and only if the action of the superoperator on the conjugates and actually I'll say it somewhat more less mathematically, they're interacting in a classical way if and only if no quantum information can be exchanged via this operator e to the L t, which is generated by a trace over the ancilla of this v of t, d by dt. So this is the generator that we're looking at. And that corresponds here to one iteration of this map in the limit where tau, this little t goes to 0. So the key point is that I have a force between two things, I can have an interaction between two things, and if I require that interaction not to communicate quantum information, I can say that these particles are interacting in a classical way. Yes.
So I think it's because of the particular model for the unitary coupling machine that you only need to put the screening in there after 2 steps rather than after
Each one,
each
yes.
one.
Uh,
You might argue it's a generic model for some reason, but I think that's a true statement, isn't it?
it is. What we've argued in the paper is that this allows us to generate all possible classes of such interactions.
Yeah, I believe that.
And then we can look at the consequences of this classicality statement over all possible such channels. It turns out, again, that heterodyne saturates the bounds that you get, because it turns out to be optimal for implementing this with minimal other noise. And there's some subtleties here. For example, if I have 2 harmonic oscillators in number states, and I want to have a number-number interaction between them, well then the very natural thing for me to do would be to measure the number in one and apply it as a phase shift on the other. That's exactly what a number-number interaction looks like. And I can measure number as well as I like. There's no back action noise on the number sector. But it's in the conjugate variable. In this case, something like a phase operator, doesn't quite, be careful how you define it, that this number measurement causes error. Yes, go ahead.
So there's something strange going on here because heterodyne makes reference to vacuum noise, which is a particular statement about the having equal noise in both quadratures. But here it's a closed system, so why are you starting in? I mean,
It's not really a closed system once I put the screen in. Right, the screen is a super operator.
yeah, okay, that's
So your S is just some CP map which preserves X and P.
S is a CP map that does this.
So why not have something which measures one quadrant with greater accuracy than the other and produces not a coherent
Oh, you
state,
can.
but a squeeze state?
No. You can do all sorts of different things.
No, but what I'm saying is,
Yes.
when you say that the coherent, okay, are you making a statement that heterodyne is in any sense unique? The unique thing which will attain this bound? Because I can't see.
I know, it's not clear to me that it's unique.
No, okay, all right.
And in fact, I have no reason to believe it is.
I mean, the simplest form of S is just the identity chat.
Well,
That's what we had before.
so the thing
sorry,
about S is the identity, then it's no longer interacting in a classical way. You can show that you can send quantum information.
So it has to be what's called an entanglement breaking channel.
Yeah.
Yes, that's right. So of course we know entanglement breaking channels can always be redescribed as a POVM followed by creation of a state based on the POVM output. And so we actually know that all possible classical channels end up having to be classified based on the POVM that goes in. Now, the point here is simply that this language has been very helpful for me to be able to define something like a classical force. And as you can guess, of course, by the statement that the best way to do this that we can think of at the moment is heterodyne, and that saturates the noise bounds that we get. The consequences of putting a screen in are that you induce noise in the system. And so if you think that there exists some sort of classical interaction between two particles, then you can test for it. And you can test for it in the noise. Now this is, there are actual theories where this makes sense, where you have to worry about this. Yes, go ahead.
You probably won't be too surprised that I'm not completely satisfied with your definition, right?
Well, that's okay, but there's a wonderfully long supplemental material in which we go into great detail about the definition. So, I mean, there's some key points about it, right? So one of the key points about it is that at the end of the day, you don't look at this. Right? This was for us a helpful construction to get started. But at the end of the day, really what you're looking at is you're looking at a superoperator L operating on A and B, which is of the form Hamiltonian on A, Hamiltonian on B, and an interaction term plus other terms. And the other terms end up being of this sort of type. And you can show that the requirement that the composition of the map converge in a Trotter sense. So this map VT, remember I'm looking at something which looks like the trace over F of VT over some n composed n times as a limit of a continuous map. If I want this to converge, I require that all the terms in this superoperator of root t go to 0. So that constrains this form. And then the second point is the requirement that you develop this HAB without any information transfer.
Couldn't you capture all of that with looking at the commutation structure? So
Yes.
if you've got a quantum part and then you want an interaction with another quantum part, but through
You don't,
something that doesn't exchange, surely there should be something that's
you don't
muted
need,
in the
you
middle.
don't need
right?
something in exchanging at all. You just need to know the form of this thing, which is that it's A, B, yeah? Some operator on A, some operator on B. And given that, the choices of these additional terms in superoperator that have the Ehrenfest condition but don't allow quantum information through are quite distinct. So at the end, you don't need the channel. Well, what's amazing to us is that no matter what we do here, we can always write this version of it. Right, so there's a mapping between here and here.
Do we allow different symplectic structures on the classical mechanics?
You're asking if I could change the symplectic structure?
Yes, but you also allow that the classical mechanics is a different symplectic structure.
So I'm only allowing classical mechanics where I've got a set of canonical variables. So A's and PA's.
This is a standard symplectic structure.
Yes. So in fact, the symplectic structure shows up in our proof because we end up getting a statement about the density matrix here, which is for Gaussian states has a covariance matrix, and we essentially require the covariance matrix plus the symplectic matrix to be greater than equal to 0 in a positive definite sense.
Sorry, just the dissipative part of the Lindbladian.
So one last thing, if you want to change this, if you change the symplectic structure, you actually change this inequality. And you have to derive it from using symplectic. I don't know what the answer is. Please go.
Yeah, your Lindbladian, the dissipative part.
Yes.
Is the collapse operator just A plus B?
No, it's not. See, if I just had an A plus B collapse operator, I can actually entangle the things. So be a bit careful with it.
Right. It just looks like that. What is the collapse operator then?
Well, it has several different terms, and there's some inequality with each of the terms, such that it's classically interacting. I mean, it's of this form, but there's prefactors out here, so there's basically a matrix of terms, as it were. And the requirement that the classical correspond to terms in that matrix having a certain positive definite structure.
Mm-hmm.
So there's many different choices, right? But you can't, for example, make it A plus B. And this matrix is no longer classically interactive.
But is it easy to write down what it looks like?
Yes. I mean, it's easy to write down the remaining 1 minute that I have. No. So, yeah, it's the same. I've got it. So basically, if I label this thing here as y AA, this thing here as y AB, and this thing here is y AB. There's a 2 out front. Then this matrix Y is the thing that you're interested in. And where's the matrix equation? There it is. So what you require is that y be greater than or equal to the eigenvalue times twice I times the symplectic matrix. So the symplectic matrix, if you recall, is this object, 0, 1 minus 1. So this is the constraint you get on Y for classical interacting. And again, if I change the symplectic matrix, that would change what that constraint looks like. So another way to think about Y, by the way, because the first moments are constrained, yes, are good.
Sorry, what's the relation between eta and delta?
Where's, oh,
What's eta?
yes, so I've been skipping many steps in order to just capture the essence of it. Okay, so there exists eta. How to describe it? So if I want the screen independent picture, then the eta that shows up in here ends up coming in as, I guess, an eta squared, or no, just an eta prefactor like that. So that is to say that the stronger this is, the stronger Y has to be in order to satisfy this constraint. So as you can expect, if I increase the coupling, the measurement's going up. Measurement going up and requiring classicality, I mean the interaction going up and requiring classicality means the measurements have to get stronger.
And what are the dots at the end?
Oh, this is a super operator?
Yeah, no, at the very end.
Oh, so there in principle can be higher order terms. Right, ones that, so I've looked at things that are doing stuff on A's and B's and PA's and PB's, and then the quadratures of those objects, so the squares of those objects. In principle, you could start looking at terms that are higher order, but we don't think that they converge to anything other than 0. In other words, I haven't been able to exclude maps in which something non-trivial happens at a third order commutator, which has a continuum limit.
But you're saying you can always get this map with only the second order term?
Yes.
Right, okay. Where I is subject
And more to the
this.
point, all possible maps with up to second order terms are at this point.
Right. So
The,
we could
the
just
ones
rub-
that satisfy the interface condition. Yes, go
So
ahead.
you could just rub those out.
Yes, that's correct.
Okay.
Things get a bit more complicated when we start to now apply this to many particles. So this is just looking at two subsystems that are sort of communicating, and I ask myself, if I don't allow the communication, the force law between them to communicate quantum information, what are the consequences? It's worth mentioning that in highly asymmetric systems, the information transfer rate is extremely low. So consider again the Earth neutron system. I have my neutron beam, and I see the bouncing of neutrons quantized by a force. You know, I see their quantization of their wave functions by a force due to Earth's gravity. Right? That's communication between, in this case, the position of the Earth and its mass, and this tiny particle moving by. But as you can sort of intuitively picture, the information transfer between the Earth system and the neutron is extremely weak. And so if that information transfer was classical, you wouldn't see it anyway, because the information transfer rate is so low. So in some sense, this eta parameter is actually an information transfer rate that we can extract from the system. So what we've been doing with, actually before I go into what we've been doing with this, let me ask you, are there questions about this concept of two particles that are classically interacting? Yes.
So it's sort of, so in the Earth neutron example, it's fairly obvious that you can make the measurement term on the neutron negligibly small, and
Yes.
the one on the Earth would then be very large, but still negligible compared to everything else that's happening to the Earth.
Yes.
But the cross term is not. it's not
There's a geometry
immediately
mean
obvious to
of the
me.
two that might show up there.
Yeah, so that's not, I guess I don't have a good feeling for how that affects the neutron.
So you can work it out,
Yeah.
and you find that there's a mass scale and a time scale set by big G. And big G being very small, so this is the gravitational constant, makes all the rates pretty low. But then the information transfer rate goes as something like the following. It basically goes as big G times the density, another density, and actually this part's not really important. The key point you need to know is the information transfer rate. Let's call this thing capital information. It goes as big G, and it goes as a geometric mean of the masses, one of the geometric mean of the masses, times some other terms. And what that means is that when you have very, very asymmetric masses, it makes a very low rate. When the masses are symmetric, the rate can go up.
Yeah, but a rate for what?
Information transfer rate in sort of bits per second.
It also determines the noise.
Which also determines the noise, that's correct. Right, so the information transfer rate determines the size of its Y matrix, which determines in turn the source of the amount of noise that it uses. So if you want to make it big, then you want to choose objects that are the same mass.
So what's the general expression for the information transfer rate in terms of Y? Or whatever.
Actually, it depends not just on Y, right? But it also depends on the operators A and B.
Yeah.
Okay. And so I don't have a generic statement about it. We've only worked it out for the harmonic oscillator case. So, for example, it's possible that with spins this is different than it is for harmonic oscillators.
Maybe we should talk about it later.
I'd be happy to.
Unclear
In the harmonic,
how you
in the
define
harmonic
it.
oscillator case, the Hamiltonian term causes a normal mode splitting between the two coupled oscillators. The noise term determines the decoherence rate and the heating rate, and it turns out they're all about the same. So, in the optimal limit. So, as soon as you fix the coupling, you fix the normal mode splitting, and that fixes the heating rate and the decoherence rate to be roughly the same as the normal mode splitting on the classical boundary.
Yeah,
And
so
you also have this weird final term.
the AB term.
Yeah.
I mean, you would expect it generically, right? I could choose Y to be sort of diagonal and look for this inequality, but the generic case you have this term.
Oh, so I can get rid of it if I want.
Yes.
I see.
I'm saying if I want to look at all possible channels, I have to
Yeah,
do
I
it.
see.
The case I just described doesn't have it.
I
That's
see. Okay, right.
So, kind of what we've been doing using this, first of all, we're able to derive essentially that there's a noise for classically interacting particles, not as you wouldn't have otherwise expected. What's nice about the noise, though, is that it's something you can test for. If you don't see it, then the interaction that you observe has to be quantum. Right? It's transferring quantum information, so what else do we call it? And then we've been asking ourselves the question, well, how do you account for information beyond just the fact that I saw that particle A made particle B legal? And right now we have force, there's two particles that are interacting. But if you know anything about force laws, you know that force laws are more than just a statement that particle A interacts with particle B. Right? They're a statement that particle A interacts with particle B with a strength that decreases as one over the distance. So we had to ask ourselves next, what's the information content of that statement? Right? How does the information transfer rate change when I take into account that there's constrictions, there are restrictions on how the force law operates? So I wouldn't say that this story is complete in any way or form, but we've been able to make some progress on it, and I'll tell you briefly about that. But I can put it in some different perspective to engage the sort of problem-solving portions of your brains and ask yourself, how would you, with measurement and feedback, reproduce a 1/r interaction between two distributions of particles?
Reproduce or generate?
Well, it's measurement and feedback. So you're generating, you're sort of synthesizing something that looks like a 1/r interaction.
Is there any intrinsic interaction between particles?
So the key point is that you're assuming that all the interactions that you have are of this classical type. So there's no intrinsic interaction. So that actually was a bit of a puzzler. And we came up with one way to do it, but there are certainly many others. It's not
So
clear
in
to-
fact, the things you've been talking about, the neutron, blah, 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 means that you have, or that you've used those results already, or you're treating, in that case, you're linearizing them.
So the linearized case, where you say the two things with small displacements around some minimum, that part we did initially.
Yeah.
And now we're generalizing to the case.
I guess what I'm asking is, have you already used that generalization in some of the things you've told us? Or?
No, not yet.
No, okay.
The only generalization you really need to know about is that the statement I made here can be made general to multiple operators A and B. So it can be made more broadly speaking across many such channels, as I understand its composition of such channels. But then we can actually try and apply it to a particular case, right? Which is, again, if I have two particles and say they're interacting with one over R, how do I do that? So very simplistically, what is a 1 over R interaction between two fields? Right, well, I have if I write down the interaction, I would look at a term looks like this. There's my 1 over R interaction. These are field operators.
Why do you want to treat them as fields?
Because they don't know where the particles are.
Yeah. So R1 hat, R2 hat.
I don't find position operators to be meaningful until I know I have particles in the first place. So in one way to think about it, like let's say I have distribution of mass over here, distribution of mass over here, I want to introduce 1 over R law. Well, initially I can do a monopole estimation, right? So I might estimate the center of mass of this object. Then I might do a dipole approximation. I might estimate the dipole, then the quadrupole. Then I can do multiple expansion. That's a series of different measurements I have to make. Right? So actually the point was that initially I started thinking about, well, let me expand about these multiples. That becomes very complicated. If you know there's this fast multiple method. So in principle you can do it, but there's it actually gets quite prohibitive. It's much cheaper to instead start with a picture more like this and put it on the lattice. So you discretize it using discrete variable observation. And this goes to the sum of the sites on the lattice of essentially a number operator at site 1 and a number operator at site 2 with what's called a softening, rho epsilon, corresponding to the fact that this is on a lattice and I've taken Newton's law and softened it out a little bit. And so now, writing it this way, it's actually easy to work with, because I know what this thing is, it's just a number operator. So how do I make measurement and feedback? Well, I locally estimate all the number operators at each lattice site. And based on that local estimation, I apply feedback to all the other number operators given by my estimate of the first one. And that will reproduce via measurement and feedback the procedure. Now, in order to make a meaningful statement about force laws from here, I really have to rely heavily on this picture, because the key point, and this is really Gerard's insight, is that all this story about screens and the like maps in the saturating bound, this heterodyne bound, to measurement and feedback. And so I can use all the knowledge I have about how to do optimal feedback in order to constrain possible theories.
One in the limit that the lattice spacing gets smaller, it's going to diverge, and you're going to have infinite heating.
Well, yes, that's right. So you have to anticipate that there's going to be a length scale below which the theory breaks down. And in fact, what we're able to constrain at the moment is this length scale.
Through experiments.
I'm a bit confused. So you start with the 1 over R potential, and then you do stuff to it, and you get. I don't understand the logical.
So imagine I have a 1 over R type interaction, but for particles that were stuck to a lattice rather than
Sorry,
free
the
space.
door. I can hear.
Imagine I have a 1 over R interaction, but it's between particles that are stuck on the lattice.
Yeah.
Right? So then I get 3 terms from my original underlying 1 over R thing. I have an on-site interaction, which will renormalize away. I have an exchange interaction, which decays exponentially as a function of distance. So we throw that away. And I have a long-range interaction, which looks like number operator on one site times number operator on another site divided by the distance between them.
Yeah,
That's what I did from here to here.
right.
Then, to turn this into a classical force, this is still quantum, right? To turn this into a classical force, I need to apply a map just like I did up above. And it looks like the following. I first, at site I, or site J, let's say, I displace an ancilla field by an amount A to A. Then for this displaced ancilla field, I apply this thing, sum over, say, k not equal to j of n k p a to b divided by this distance rk minus rj plus a. And then I throw away the ancilla. So this two steps, producted over the j's, where each one of these is its own special ancilla xj, j, reproduces the dynamics you expect from this in the Ehrenfest sense above, but adds the noise in the other sense as well. But of course,
So it's not your objective to derive a 1 over r.
no, it's to say I observe phenomenologically 1 over r. What
Okay.
assurance do I have that this comes from a quantum theory? Right? I mean, obviously, if gravity is the particular case, we think gravity is going to be quantum, I expect it's going to be quantum, but how do you show that it must be, right? So there's several answers to that question that have come up in the past. One answer is, if I see gravitational radiation, it must be quantum. But yeah, it's spontaneous emission, we have to, it has to have single photons, or single gravitons.
Assuming that you're restricting your possible physical theories to quantum and classical.
Well, I'm really asking the following question. Can I show that gravity must be conveying quantum information? That's really the question. So for me, what is a quantum
Well,
theory? Quantum theory is a
assuming-
theory which
Well,
communicates
well,
quantum information.
can you entangle things with gravity alone?
Sure.
Yeah.
Okay. Yeah. I mean, I guess that some people think that quantum gravity is going to break quantum mechanics. In that case, your options are not just a quantum theory or a classical theory. That something could be something completely different.
Yes, I'm really only talking about the quantum communication component of gravity, whatever it is. So I'm allowing for the moment that local quantum mechanics at sites A and site B are well defined. And that we have some sense in the low energy sector that this is true. Now, of course, I would contend, though I don't see any experimentalists in the room,
You're still on air.
that I would contend that if you look at current experiments, they've tightly constrained local quantum effects to be roughly correct. That whatever corrections that should exist that we haven't yet seen. And so we have a pretty strong assurance that this quantum information story at the local value is correct. And now we're trying to say, well, how can we confirm that it must be correct over longer scales, and in particular with respect to forces that we don't fully understand? It's worth mentioning that we have an extension to this approach, having nothing to do with gravity, but asking a very similar question. So let's say that I have a quantum simulator. And in this quantum simulator, I have all these different things interacting with each other, and I've produced some wonderful many-body state psi. And now I'd like to know, do I require a quantum description of this system, a non-local quantum description of this system? And if so, can I prove it via an experiment? So the way I like to think about this is, can I prove that this many-body system is not just locally quantum, but it's globally quantum? And so you can actually take this picture and draw a direct analogy, where you say, let me take a test particle up here and another test particle up here, and I use the test particle to create an excitation in the system, which propagates through. And then I try and have this excitation move this particle. So I induce, via the many-body system, an interaction between two objects. And then I can look at the noise on that interaction. If the noise is below this above bound, we haven't really described in detail, but it's in the papers, then I can confirm that this many-body simulator is communicating quantum information.
Well, at least that, but assuming this model for the classical interaction.
No. The whole point of the channels approach. So initially I started with this sort of quantum information picture. Then we moved to a broader section of all possible channels that do this. So it's a proof of all possible channels. It's not It's not a proof over just this example.
Well, but I guess my point is that this particular, like this model here, for example,
Yes.
like if you're not sure about that your experiment obeys quantum mechanics, then how sure are you that it has a 1 over R potential? I mean, there are many things that you could start to question about to say, well, could I come up with some locally
Yes.
quantum but classical, thing which fits within my experimental error, rather than assuming that it's exactly has this form.
Yes, I completely agree. Again, the point here is to say, as you refine your experimental results, at what point can you say, based on what you've observed, that there is a quantum communication via the interactions you see? That's really the point. Now, you can apply it in principle to gravity, that's one of our hopes, but you can also apply it to other systems, like, for example, a many-body quantum simulator. Can you confirm that many-body quantum simulator, whatever interactions it has within it, are in fact conveying quantum information down the simulator? And so if you want to, for example, verify your quantum device in a way that is, in some sense, as robust as you can make it, this would be, I contend, a way to do it.
D-wave quantum computer.
Well, let's say hypothetically that you agreed that the D-wave quantum machine has local devices that are described by quantum mechanics. Something like a flux qubit. Not a very good one necessarily, but But then you could ask, well, okay, but is this interaction that I've induced between them, does this actually require a quantum mechanical description, or is this semi-classical rotor model going to suffice? How do you disprove the semi-classical rotor model? Well, the answer is you look for the effects of the semi-classics, which in this case looks like noise. And if you can bound the noise below the value, then you've got, yes, go ahead.
But what about if you have both?
Both classical and
both,
quantum.
Yeah, and they're both, they're both present and they
So-
do different things. And
So the key point is that this type of inequality, just like a Bell's inequality, tells you nothing if you don't violate it. If you violate it, then there's got to be a quantum channel.
All right, so
If you haven't violated it, good luck. So anyway, I'll leave there
Right.
and just say that I've been very intrigued by the questions. How do you prove something about the optimality of a channel? And how do you prove things over all channels? And I have to say that we've made some initial stabs at this with some minor success. But I will say that I would like to think that the quantum control community has a lot more to say on this topic than we've been able to take advantage of at the moment. I'd love your feedback. Thank you.
Okay.